All right, good afternoon. I'm Austin Gadient, CTO and co-founder of Vali Cyber. And I'll just start off by telling you a little bit about myself. So previous to co-founding the company, in my undergrad and graduate degrees, I was on a CTF team on both colleges. And I served in the Air Force for a few years and worked on satellite cybersecurity, both for satellite ground systems and satellite flight systems as well. And it turns out satellites tend to run Linux systems on their flight computers and on the ground systems as well. So I was working on a lot of defensive Linux security, which is how I ended up founding the company focused on Linux security in the first place. And today we're going to be talking about runtime security in the cloud. And if you think about runtime security, this is security that happens while processes and code on a system are running. So we're not talking about container image scanning or virtual machine image scanning. We're talking about taking a look at the operating system functions and system calls and that sort of thing. We're also not talking about API security. It's typically maybe that host-based protection that we're discussing. And when it comes to the cloud is almost entirely made up of Linux systems. So runtime security in the cloud is really runtime security for Linux in most cases. And the original technologies that these tools used to gain information about what was happening on a Linux system were kernel modules primarily, and audit D as well. And so there are some challenges with these technologies. So kernel modules have this issue where there's a lot of variability in the Linux operating system. So you have lots of different versions of the kernel. You also have different distributions of Linux, Ubuntu, Red Hat, Debian, so on and so forth. And the kernel modules are very specific to that combination of kernel version and distribution of Linux. And so providing a kernel module-based solution becomes a challenge when you're trying to do it for a very diverse competing environment across lots of different customers. The other challenge with kernel modules is that when you deploy them, they can cause instability in the kernel if they have some sort of bug or issue. So if they crash, they cause a kernel panic, which can destroy an operating system. If you think about where Linux is used, it's typically used in environments and enterprise environments running the revenue generating applications and services for a company. So any sort of instability is totally unacceptable. And then audit D just has the problem that it's relatively slow. So it slows down systems a lot. And Linux systems are typically quite busy. They're either web servers, databases, messaging queues. They're processing many, many different events. And so as a result, they need to be quite snappy and quite fast to be able to provide those services in a meaningful and impactful way. So enter eBPF, this new technology. So if you're a red teamer and you find yourself red teaming and trying to gain access to cloud workloads, you're probably going to run into an eBPF-based security tool. And the reason for this is lots and lots and lots of vendors are moving over to this technology. And there are some good reasons why. So in contrast to audit D and kernel modules, eBPF tends to be more performant. So it tends to have pretty good performance characteristics. Of course, this depends on the eBPF programs that are used. It also depends on the workload that's being used as well. But typically speaking, it's going to have good performance, and it also has some stability guarantees. And the stability guarantees are provided by something called a verifier. So eBPF programs get compiled into bytecode, and they get verified by a verifier that exists inside the kernel. And the verifier ensures that the program meets certain specifications. So it has to terminate. It can't have any infinite loops or anything like that. And as a result, the verifier ensures stability. So the eBPF programs aren't going to crash your kernel or cause any sort of instability, which is really, really important for any sort of monitoring or security tool on a Linux system. However, this tool wasn't initially built with security in mind. It was built as a network diagnostic tool. And what happened throughout its development is people realize we can attach eBPF programs to more things than just packet events. We can attach them to system call events as well, and essentially instrument the entire operating system, the entire kernel, try to understand what's happening at a lower level. And so the tool was not built initially to be used for security applications. Security applications are, of course, challenging because people are constantly trying to break whatever you're doing. So here's how eBPF essentially works when it's used in a security product. So you have some sort of user space process, and that user space process is going to load eBPF programs into the kernel. It's going to attach those eBPF programs to certain events, whether they be packet events or certain system calls being executed. And when those system calls get executed by some other process on the system, the eBPF program has an opportunity to take a look at the arguments to the system call. And it can log information into what's called an eBPF map. The map is a data structure that allows the eBPF programs to communicate with the user space process. And through that communication, the user space process can figure out things like a file being open on the system. It can see the path that was being accessed. And then it can decide to take some sort of response. It knows what process accessed that file. Maybe it kills the process if it thinks that the access is malicious or something like that. But there are challenges with this architecture. So the first thing is that eBPF programs are inherently non-locking and reactive. And so what that means is what they can really do, they can log information. So they see a system call, they can log information about what happened, but they don't have a chance to deny that action. So it's not like they can wait for the user space agent to analyze the system call information and then say, no, this shouldn't happen, and then deny the operation from happening. They just have to allow it to happen and log something that happened. So you can imagine if the event is something like deleting a critical file, killing a critical process, that event is going to complete. And you're just going to log it after the fact, but you don't have a chance to stop it ahead of time. There are also a lot of non-standard system calls that can be used to do things like open a file on a Linux system. And this isn't really an eBPF problem, but it is a common problem in tools that do system call monitoring and that use eBPF for system call monitoring. Another architectural challenge is that eBPF maps are limited in the amount of memory that they can use. So they're ultimately constrained by the amount of memory that the operating system uses, but they're also constrained by whatever default settings a product might use. And if the user space application is not able to read what's happening in those maps fast enough and process them, well, those maps can fill up. And then when they're filled up with a bunch of information, the next events just get dropped. And so the attacker can execute events without actually being detected or noticed. And then, of course, the verifier is a very complicated piece of code, and it has lots of CVEs against it because it's doing complex parsing and analysis of these eBPF programs. And so it leads to a lot of different local privilege escalation exploits and vulnerabilities. So we're going to run through a couple different demos of attacks that can be launched against eBPF-based security tools. The example tools that we'll be using are Falco and Tracy. Falco is produced by Sysdig. Tracy is produced by Aqua Security, and they're both open source tools, so you can download them from the internet, use them however you would like, test them out. And the agents in these examples are going to be running inside Docker containers, and the host VM is an Ubuntu 2204 VM. It's got 2 gigs of RAM and 2 CPUs that we're going to be running these examples on. So what is the first thing that you can do? Well, you can just kill the agent. And you can kill the agent if you have the appropriate permissions to send signals to the user space process. Typically, this requires some sort of privilege to be able to do that, to send those signals to the user space process. Of course, it's noisy to kill an agent, and someone might notice that you're killing an agent. And there is a possible mitigation to this. So it is possible for an eBPF program to deny an event from happening using something called BPF override return, which allows them to override the return code of certain functions in the operating system. But the problem with that is it's only available on x86 today. So ARM systems aren't going to be protected. So a newer kernel version would be required with an update that supports running this function on ARM to have that mitigation in place. So here's an example of doing this with Tracy. So we have Tracy running at the top. And we're just going to sudo su, make ourselves root, kill the process, and you can kill it, no problem. It's a user space process. You have root permissions, you can kill it, and then you can execute whatever behavior that you want. Same thing with Falco. Nothing fancy. We're just going to sudo su, kill it, and instead we can do whatever we want. So the challenge here for the attacker is you have to have privileges to do this. So what if you could kill an agent without privileges? We'll get to that a little bit later in the talk. But in the meantime, another option that an attacker has is using Simlinks to access resources on the system. So Simlinks are an alternate way to access file system resources on a Linux system. And they work essentially by creating another path that can be used to reference the same file on a system. And the way these tools work, Tracy, Falco, and a lot of these other system call filtering tools, is they essentially do pattern matching. So they're going to look at a file you're accessing, how you're accessing it, perhaps the context in which you're accessing it, to determine whether the access is malicious or not. And so if you can change the name of the file using a symlink and access the file, that symlink, you can potentially bypass the defenses. Tracy didn't have this problem in my testing. They use something called KB probes to attach to LSM hooks. So they're being notified about a file being accessed after the file has been opened. So they don't have the ability to notify when a file that doesn't exist was attempted to be accessed. But if a file is successfully accessed, they don't have to worry about resolving symlinks or anything like that. Of course, they do need to be on a system where they have the kernel headers so that they can use KB probes to attach to these specific events to do that. And Ubuntu 22.04 is a popular system. So in my specific examples, they did have that capability. So we'll do this with Falco. The first thing that we'll do is we'll just cat this file, and we'll see that if we do that, we get an alert. So if we just access the file itself, we get an alert. But if we make a symlink, and we cat that symlink, no alert. So we can access the file. We didn't get detected just because we changed the way that we were referencing the file. And that new file name doesn't match the pattern that was used by Falco to do the detection. So just like symlinks are an alternate way to access files on a system, you can use alternate system calls to open files on a Linux system. And two uncommon system calls that could be used besides the common open and open at system calls would be open by handle at and IO uring setup. So IO uring setup is a relatively newer system call. Open by handle at is older, just doesn't get used very often. And these open by handle at specifically requires an extra permission, although IO uring setup does not. So you don't need any sort of special permissions to use that system call. And the reason this works and using these alternate system calls works is because the eBPF-based security tool didn't attach to these other system calls, so it's not able to know when they happen. So you can just avoid that logging that happens when the eBPF program logs something to the eBPF map. So we can see this with Falco. We'll go ahead and cat that file again, and we'll see that we got an alert. But we run this alternate program. In this iteration, we're just going to use the open by handle at system call. Then we can run this program again. And this time, the program is going to use the IO uring system call. And when it accesses the file, you don't get any sort of alert. You're just able to access the file without any problem. Now, there's a cool mitigation that Falco has for containers. And one of their detection techniques is that if you create a new executable inside of a container while the container is running, they'll alert. Basically, you're dropping a new executable into the container. They'll alert on that because they know the executable was not part of the base container image. So that example that I used doesn't work so well for us if we run it inside of a container. And we get an alert about a shell, but that's just the shell that we're using to run the actual command. So if we try to use this program inside of the container, we get an alert. That's that alert about dropping an executable into the container. But we can bypass this by using LD preload. So instead of executing an executable, we just load a library into memory and execute that library. And you can set up the library so that it has initialization constructors so that when the library gets loaded, it automatically runs a function, and then you can use that function to use the IO uring sys call and access the file. Okay, next thing you can do. It's a little bit more complicated. Resource exhaustion. I like this one a lot because it's really hard for someone to patch because it's based on the fact that the eBPF maps are limited in the amount of memory that they have. And essentially what you do is you take a program, you have it execute a bunch of bogus system calls that you don't really care about in an infinite loop. And it's going to fill up the map with a whole bunch of these bogus events. and then you actually execute the malicious behavior that you want to execute. And the tool can detect when events are being dropped, but it doesn't actually get to process the events that you executed while events were being dropped, which allows you to bypass the detections. And there's a CVE that uses a very similar concept for Falco. In the write-up for the CVE, there's no POC available for it anymore. But in the write-up, they said they used about 256 processes per CPU. I found that that didn't work in my setup. I had to use one process per CPU. Then this attack technique worked quite well. So we'll go ahead and do this with Falco. So once again, we'll access the file. We get the alert. This time we'll run this program called Exhaust. And what Exhaust does is it spins off 2 child processes, and they fill up the eBPF maps with a bunch of bogus system calls. Then they access the file without triggering an alert for accessing that file. But they do trigger a different kind of alert. So you saw this debug level message talking about events being dropped. And so the challenge with this sort of detection is that you can think about a SOC analyst taking a look at this alert alongside all the other alerts that they have to investigate. Are they actually going to take this one seriously? Because this is a type of alert that can happen anytime the system gets relatively busy. So it looks like pretty benign, innocuous behavior. It doesn't tell you anything about anything malicious that could be happening on the system. It's just a notification that there was a lot happening on the system. And so the eBPF-based tool wasn't able to process everything. And we can do the same thing with Tracy. So we'll execute the cat command just to show that if we access this file, we get an alert. Now we run exhaust, and this time we target Tracy. So Tracy is going to try to, or the exhaust program is going to try to open that file. And you'll notice that there's a difference between Tracy and Falco. So Tracy doesn't limit the size of its maps in the same way that Falco does. So the reason why the example works very quickly with Falco is by default, Falco limits their maps to only being 8 megabytes. But with Tracy, it uses the entire memory of the system. So we have to run this attack for a period of time to fill up the memory. And you can see the memory usage of Tracy continuously going up as we execute more and more of these bogus system calls. And eventually, kswap D starts, and this is when the system is really constrained for memory, and we're able to access the file without any sort of detection. Now, I mentioned earlier, what if there was a way to kill one of these processes, one of these agent processes, without extended permissions? And this is how you could do it, at least in the case of Tracy. There's something in Linux called the OOM killer, or the out of memory killer. And so if you access or you run this exhaust program for a long enough time, they'll cause Tracy to use up so much memory that the operating system just kills the process. And then you could execute whatever malicious behavior that you want, and essentially tamper with the agent in that way. Okay, so here are some harder things to do. One would be kernel exploits, and specifically exploits of the verifier that I talked about earlier. Now, there are a lot of good POCs out there for some of these vulnerabilities. So in my examples, I'm just going to use the POCs, and obviously using someone else's POC isn't a challenging thing to do, but developing the exploit in the first place, that's the challenging thing. So if you wanted to go write your own kernel exploit, that can definitely take some skill and some time. Another thing that's important to note is that on kernel versions below kernel 5.8, depending on the setup, you're probably going to need capsysadmin to use eBPF programs in the first place, and you're basically root at that point. So it's not that useful to have this capability if you have capsysadmin already. But on newer versions of the Linux kernel, all that is required is capsys BPF, which is a lower capability requirement than capsysadmin. So if you wanted to escalate your privileges from capsys BPF to having something more privileged, you could certainly use these kernel level exploits to do that. Now, the second thing that you can do is you could actually tamper with the maps directly. So the eBPF maps themselves are global resources. And because they're global resources, anyone that has the ability to access the maps, to write data to the maps, to modify data or delete data from the maps can do that at will. So you don't have to be the process that created the map to add data to it or tamper with it. And as a result, we can launch an attack if we have the appropriate privileges to just target and tamper with the maps that are used to communicate with the eBPF program, and the user space process. And in the example of Tracy, we're going to attack the events map. In the example of Falco, we're going to target the syscall exit TA map. All right, so let's see this in action. So what we're going to do is put together the kernel exploit. I'm going to run the kernel exploit POC, and we're going to get root on the system. Now that we have root, we're going to delete all the keys from that map for Falco. Now we can access this file as much as we want without any sort of alerting. You can see that the agent process is still active. We haven't done anything to damage the agent process itself. We've just tampered with that map. So it looks like the security tool is functioning properly, but it isn't anymore. It's not able to detect attacks anymore since we went ahead and tampered with that map. And we can do the same thing with Tracy as well. So once again, we'll run that kernel exploit POC that will allow us to get root on the system and extend our privileges. And now that we have extended privileges, we can go ahead and access the file. Well, before we run the delete keys, we'll access the file. You can see that there's an alert. Now we'll run the delete keys program, and that will delete the keys from the map. And now we can start accessing the file and executing whatever malicious action that we want for as long as we want in perpetuity. And so we have disabled the security tool, not by attacking the process itself, but by attacking the data structure that the process uses to communicate with the eBPF programs. Okay, and an honorable mention of a type of attack that can be used against these sorts of tools is TOCTAL, or time of check, time of use. And the way TOCTAL works is essentially there's the check that the eBPF program does when it logs data into the eBPF map. And then there's the time that that data is actually used. And so there's essentially a race condition where the attacker can modify the data that's logged by the eBPF program after it's been logged. So the file that actually gets accessed is different than the file that got logged and that got detected and alerted on or not alerted on by the user space application. And the reason that this is just an honorable mention is that these attacks are pretty hard to pull off because they're very timing intensive. And so depending on the workload itself, it's hard to make these attacks reliable. Although there was some work done to do this, there was some work presented at Black Hat and DEF CON for CVE, these two CVEs that are presented on the slide. And they were very situation specific CVE. So there were certain requirements that needed to exist in the environment, certain file system types that needed to be used to be able to pull off this attack reliably. So this is definitely a more challenging attack to pull off. And if you can, it's wonderful, but it's generally not the most reliable method compared to the other methods that we've gone through. So what were the contributions of this work? We put together a comprehensive list of different ways that you can attack eBPF-based tools, and that was really the goal here. There's been a lot of fantastic research done by the community to determine and show how you could potentially bypass these tools. And this work was really about pulling that all together and putting it in one place. There's a GitHub repo that's public. So if you want to go access that GitHub repo, you can go see the examples that were used in the talk. You can also run through the examples yourself and see if you're able to get the same behavior. The resource consumption attack against Tracy was novel and new, as were the map tampering attacks against Tracy and Falco. Those were novel, new attacks against those specific tools and programs. So I'll take any questions.
Thank you so much for your talk. I do have a few questions here. One is related to a link that actually someone else posted about eBPF for Windows. Have you any experience with that?
So I have not used or had a lot of experience with the eBPF for Windows, although you do have the Windows subsystem for Linux. So eBPF can be used in that environment. It's possible to present these sorts of attacks against eBPF-based tools in that environment, although a lot of Windows EDR's tools are not going to use eBPF. It's primarily used for Linux systems, and Windows-based tools are going to use Windows-based APIs to interact with the kernel and gain information about files being accessed and programs being executed, so on and so forth.
Have you ever seen any malware actually using eBPF itself for nefarious purposes?
Yes. So there are two actually good examples of this. One of them is called Symbiote. The other is called BPF Door. So you can Google those specific malware samples. But essentially what they do is they use BPF to bypass firewall rules. So BPF programs can be loaded into the kernel before the firewall does its check on a packet. And the BPF program can process that packet and do things like notify a user space process so that the user space process knows to change the firewall rules so that it can briefly communicate with its command and control server. And so it's typically used as a way to gain stealth and to be able to communicate with the command and control server in a more stealthy way.
When it comes to those exhaustion attacks that you highlighted, would you have any other recommendations on defending against that or realizing that that actually happens?
Yeah, so exhaustion attacks are really, really tough because, again, they're based on the specific architecture of eBPF, and there's only so much memory a system can have. So if the attacker is able to fill that memory up, you're in trouble. So one thing you could do is if you're able to use C groups effectively, you could limit how much CPU certain processes are able to access on the system. And so that could limit the amount of system calls they're able to access to an amount that is tolerable and something that can be handled by that user space agent. I think the other thing that you can do is instead of limiting the size of the maps themselves, you could increase the size of the maps. And that way it takes longer to fill them up. But this, of course, just causes the attack to take longer. It doesn't necessarily stop the attack from happening in the first place.
I have another one. How would CrowdStrike react to an eBPF-based rootkit? Do you have any idea?
I have not tested CrowdStrike with eBPF-based rootkits, but I do know that eBPF tools typically tend to be more stealthy. So it could potentially be a way to bypass various EDR tools, not just CrowdStrike, but any sort of EDR tool on a Linux system. And that's typically why BPF gets used for firewall bypasses, is also gets used to stealth to avoid antivirus and EDR tools.
And the last question that I have is, do you have any additional resources that you could recommend for people who are completely new to eBPF and not really know what it's about?
Yeah, 100%. So that repository that I linked in the slides, that has a list of resources in it. So on the main README page, there's a whole bunch of resources about bypassing eBPF tools and using eBPF for malware and security uses of eBPF. And then there's just a lot of good blogs online about how to use eBPF programs and how to build code with eBPF programs as well.
There's one more question. Would this be obfuscated even in prefetch or shellbacks investigations when looking or changing the file? I'm not really sure what that is about, but do you have any thoughts on that?
No, I don't quite understand the question, but
okay.
Yeah, let's just pass on that.
That's fine. All right, I think that's about it. Are there any other questions for the people here in person? No? Okay, thank you so much for your talk.
All right, thank you.